As we've seen, matrix transformations allow us to describe functions t going from Rn to Rm. In this section, we want to focus on just specifically transformations going from R2 to R2 so we can visualize their effects geometrically. We've done this a bit already in previous videos, but we're going to be kind of more specifically focused on that here. Matrix transformations provide a convenient way to describe geometric operations such as rotations, reflections, scalings, and other transformations used in computer animation. Recall that the matrix transformation is defined by T of x equals AX. For a 2 by 2 matrix, A equals ABCD, every point in the plane is moved to a new location. The matrix describes how the entire plane is transformed. Remember, the columns of A tell us where the standard basis vectors go. So A equals T of E1, T of E2. I'll just remind you, E1 is the vector 1, 0. E2 is the vector 0, 1. Understanding the movement of E1 and E2 helps us understand the entire transformation. We've already seen that matrices can describe rotations, reflections, and scalings. More generally, matrix transformations can create important geometric operations. Our book has a really nice activity, Activity 262, which explores how changing the entries of the matrix change the geometry of the plane. I actually want to kind of switch over to that so we can take a look at it a little bit together. So we have that activity here, and you can see what the setup is. We are given these sliders for A, B, C, and D, and they essentially allow us to adjust what that transition matrix is going to look like. And what we're also shown is this little square, this 1 by 1 square drawn in the plane. And so as we make adjustments to A, B, C, and D, we're going to watch that square get transformed. So if we started, for example, with the matrix, and right now, by the way, the matrix is set so that A is 1, B is 0, C is 0, and D is 1. And so that essentially is saying 1, 0 gets transformed to 1, 0, 0, 1 gets transformed to 0, 1, and so nothing changes. And we can see that that square on the right and left look exactly the same. If I were to change A to 2, what you can see is everything in the horizontal direction gets scaled by 2. I haven't changed anything else, so nothing in the vertical direction has changed. If I now make D also 2, now I've scaled both the X and the Y, the vertical and the horizontal directions by 2. So this has totally scaled everything up by 2. That square, that 1 by 1 square, is now a 2 by 2 square. Just to show you a couple more examples, if we looked at the matrix where A was 0 and B is 1, and C is -1, and D is 0, you can now see that what we've done is rotated our box by 90 degrees in the clockwise direction. So 0, our original vector 1, 0, our original E1 vector, I should say 1, 0, moved to 0, -1. Our vector 0, 1 moved to 1, 0. So those both rotated 90 degrees clockwise, and therefore that box and every point in the plane would rotate by that amount. One more example. Let's make A1, B1, C1, or excuse me, C0, and D1. You can see we've kind of slanted or skewed the plane here. So by making adjustments to B or C, you can get some other kinds of transformations going on besides just scalings and maybe some reflections and rotations. So I encourage you to play around with this activity, play around with these sliders, and go through the rest of these examples, and you can kind of get a feel for what what the different adjustments to those a, b, c, and d values would do to points in the plane.